morning to all. Today I am going to explain about directional drilling. So, what is directional drilling? So, directional drilling is a practice of deviating the well bore towards a direction to reach the reservoir. So, what is the difference between vertical and a directional drilling? Vertical drilling will be coming, the hole will be straight to reach the reservoir, but the directional drilling will be like a slight incline. That means it will be coming straight. From here, it will be deviating towards the reservoir. See, if this is a reservoir, you are getting a vertical section. From there, it is deviating to reach the reservoir. Okay, so we have multiple applications of directional drilling. So what are they? Let's see them. So these are the applications of directional drilling. The first one is multiple wells from a single location. Next one is inaccessible surface locations. Third one is multiple target zones. Fourth is sidetrack. Fifth is core drilling. Sixth is solvent exploration. And the seventh one is relief well. And eighth one is river crossing applications. Now I'll explain one by one. So the first one is sidetracking. What is meant by sidetracking? So if you are drilling a vertical well, suddenly the pipe gets stuck or a bit gets stuck, which you can't remove it from the well. So what do you have to do at that time? You can't simply leave the well as it, right? Because you have a big amount of reservoir, you have a big amount of oil inside it. So what do you have to do? You have to somehow do something to take out hydrocarbons from it. So what do you have to do? I'm just going to I'll explain from here. See here. So this is the normal well where you have drilled. So here your pipe got stuck. I'm doing multiple operations to remove this pipe stuck, but I couldn't do it. So what I'm doing, I'm just going to drill a well, and just from there, I'm just going to deviate the well. So you can ask me how you can deviate it. You will be having casings here, right? So what you have to do to deviate the well, you have to do a milling operations from here. From the casing, you have to do a milling operation just to create a window in that casing. Okay, so if you are creating a window, from there you can deviate the well. You can deviate the well like this, and you can reach the reservoir which is beneath this formation. Yeah. And the second one, multiple wells in one offshore location. So if you are drilling in offshore, you need some platforms to drill it, right? It is not a land to stay on that location or anything else. So what you have to do, you have to put some platforms for it, right? So for that, you will be keeping some TLP or duration or anything else. You have multiple platforms, right? So if you are having in a location you have multiple reservoirs. That means 7 to 8 reservoirs at a single location or an area. So if you have like that, you are not going to drill a single vertical well or multiple vertical wells for the different reservoirs in the same area, right? So what you have to do, I'll put a single platform on the offshore location. From there, I'll put a main well or a mother well. From the mother well, I will be deviating multiple wells. I'll be putting multiple wells from the mother well to reach the reservoir. From here, you will be having one reservoir here, another reservoir here, and third reservoir, and multiple reservoirs are there. So I'm just drilling a multiple wells from a single mother well. Are you clear? That is multiple wells from one offshore location. So this creates, you have many advantages of it. Because you are reducing the cost as well as the environmental impacts of this location. So if you doesn't have this, what you have to do, you have to put one vertical well here, another vertical well here, another vertical well. It will improve the cost, right? You will be having like transportation costs, and you have to rent another platforms for it. So that will increase the cost as well as the manpower, and also the environmental implications will be more, right? So we are doing this. We are eradicating that disadvantage by using these multiple wells in a single offshore location. Yeah. And then is horizontal wells. So I'll say that you'll be having multiple advantages of drilling a horizontal well. So for example, if you have thin bed reservoir, please listen carefully. You have a formation which is of very thin. Okay, you have a formation which is of very thin, and it has hydrocarbons which is profitable when you are extracting it. So, if you are putting a vertical well in it, do you think that you can extract the whole hydrocarbons from that formation? No, right? Why? Because the transition of this well won't go beyond the boundary of your reservoir. So, and also it is not giving communication for the whole reservoir. So, what you have to do at that time? So, my solution is to drill a vertical well. Sorry, to drill a horizontal well which gives full access to the reservoir. Okay, which gives full access to the reservoir. Normally, you'll be having permeability or vertical fractures will be like this, right? The fractures will be like this. So, if you are putting a vertical well, it won't connect the fractures, right? If you are drilling a vertical well, it won't connect the fractures. But when you are drilling a horizontal well, it will connect all the vertical fractures in that formation, right? So, when it connects it, these vertical fractures, from these vertical fractures, your fluids or your hydrocarbons will flow into the well, horizontal well. So, you will extract more hydrocarbons from the thin reservoir into your horizontal well. So, this is the main advantages of your horizontal wells. And the next one, salt dome drilling. What does mean by salt dome drilling? In some formations or in some areas, you have salt dome beyond it, beneath it. So, is it possible to drill an area where you have salt dome? It is possible, but it is not advisable. Because salt, right, you are drilling with iron particles or carbon particles, right? So, when you drill beyond that salt or when you drill in that salt, your drill bit or your drill string or anything will get corroded. Because when you get your material exposed to salt, it will get corroded, and also the salt is not that much dense, right? So, when you put mud into it, it will create a loss circulation. The mud will go into the salt and it will collapse the formation, right? So, it is not advisable to drill in a salt dome. So, what you have to do, you just want to drill in the salt dome area. Beyond that, you have to go beyond that and you have to drill a vertical well from here, and then you have to deaerate the well and you have to fetch the hydrocarbon which is under the salt dome. Here, so this is your hydrocarbon area which is under the salt dome. So what I am doing, I am going beyond this area, I am going beyond the salt dome area, I am just drilling a well here, and then I am deviating, and then I am fetching, I am deviating the well bore, and I am coming to the reservoir to fetch the hydrocarbon from this reservoir. Yeah. And the next one is the main application, the reaching inaccessible location. For example, if you have a reservoir under a city or a village, or you can say below our university you have a reservoir, what will you do? So, will your university or will your city administration will you give permission to do a drilling in this particular university or in this particular area? Will they give a permission? They won't, right? So, putting a drilling rig or a manpower in a polluted area or in a populated area, will they allow it? No, it won't, right? So, what you have to do, you have big reservoir under the inaccessible area or under a building. So, what you have to do, you have to go beyond that inaccessible area. For example, we have a building here. Okay, so you can't drill a vertical well here because we have building. So what I am doing, I am just going to find an area which is far located from your building, and I am just going to start drilling from here, and then I am repeating a well and I am reaching the reservoir which is beneath your building. So you can fetch the reservoir or we can fetch the hydrocarbon from the reservoir. You can produce the hydrocarbon from the reservoir which is under a building or a city or a village or anything you can use. And the other one application is relief well. So what is this relief well? Have you ever heard of it, relief well? No, right? Okay, I'll explain. So you are drilling a well. You have a reservoir You are drilling a vertically. Okay. Suddenly you get a kick. So what is meant by kick? What is meant by kick? So when the hydrostatic pressure is lesser than the formation pressure, what will happen? The formation fluids, the fluid from the formation will enter into the well, which is called as kick, right? So if it is not controllable with primary or secondary, okay, you are trying to control the kick with primary well control and secondary well control, but you couldn't control it. So what will you do it? You're going to just leave the well or you're going to close the well. You couldn't, right? Because you have a big reservoir under it, which gives a huge profit. So what I'm doing, I will drill a well far away from the lake, and I will deviate the well, and I won't go to the reservoir. Instead of it, I will deviate the well in that vertical well. I'm not going to the reservoir. Instead, I'm going to deviate the well in the vertical well. Very clear? So what I'm doing, I'm just pumping drilling fluids into it. Right? Whatever drilling fluids I'm pumping in, it is not enough to control the kick. So what I have to do, I have to pump more drilling fluids, which is not possible in a vertical well. Right? Because I have already closed with BOP. Right? I have closed the well with BOP. Now what I'm doing, I don't have any space to pump fluids inside or drilling fluids inside, right? So what I'm doing, I'm drilling a relief well. I'm going to pump drilling fluids from this relief well. So I'm getting a space to pump drilling fluids from another well. So you have already have drilling fluids here. Plus you are going to send drilling fluids from this relief. So this mud plus the mud in the relief well will control the kick, which you can fetch the hydrocarbons from this reservoir. Okay, so once you control the heat from here, you can close this one, or you can just close here with the help of packers, and then you can start drilling with this, or you can start drilling, or you can start producing from this relief well or your production. Sorry. Okay, here. Then fall drilling. What is the fall? So due to some tectonic activities, your formation may get separated. Okay, I've seen this. This is the same formation, but it gets separated. But if you see this, these are same formations, but you have reservoir. If you have hydrocarbons in a single fault zone, in this zone, because you have a high trap here. I mean trap. What is the cap top or trap? Cap top is nothing but it will close the hydrocarbon in a single formation, or which won't allow the hydrocarbons above that cap. Yeah, right. Okay, so you see here we have the same formations here, but it is separated by means of some tectonic activities. So we have hydrocarbon here. You just want to tap this hydrocarbon. So you see here, you can't drill a vertical well here because we have a cap top here, and you won't get the whole hydrocarbons with a single vertical well, because it won't give communication for the whole reservoir. Right? So what I'm doing, I'm just going to drill a directional well. I'm just going to drill here and then going to deviate the well towards this reservoir. So when I drill like this, I will get the whole hydrocarbons from this reservoir through this directional well. Yeah, that is fall drilling. So multilateral drilling. It is same way like what you have seen on multiple wells from a single offshore location. You will put a single well. From there you will drill branches of wells. Okay. See, they have drilled a single well, and they are putting a multiple branches. Right. This will be also the same advantages of what we have seen in multiple branches from multiple wells from a single location. Multilateral wells or wells that have more than one branch radiating from the main borehole. Each branch can drain a separate part of the reservoir and produce into a common single well. I does not explain that. I will explain the later class. Okay. 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 So now we have seen the applications of directional drilling. Right? Now we can see directional drilling profiles. So how many profiles we have in directional drilling? Anybody can tell it? No. Okay. We have three profiles: L profile, S profile, and J profile. Okay. So first we can see about L profile. This is L profile rational. If you see this, so I'll say the branch first. See here, for a rational you have one vertical section, right? From here to here we have one vertical section. From there you get a built-up section. From here you have a tangent section. So why this name came for this one? So as it is vertical, you are saying as vertical section. From here, your well starts to deviate, right? So the point at which the well starts to deviate is called as kick-off point. Kick-off point where the well starts to deviate. Have you seen this point? This is your kick-off point. And this is your build-up section. What is this build-up section? Tell me, what is the build-up section? So from the kick-off point, your angle starts to increase, right? The angle of deviation starts to increase, right? When the angle starts to increase till the angle ends. Okay, that is called as build-up section. From here to here, the increase of angle is called as build-up section. So you can say this is also increased now. You're not telling this as a build-up section. This is not a build-up section. Here you are ending the angle, but here you are maintaining the You are maintaining the final angle in this angle section. You are not increasing. You are just maintaining after this. So this is the start of build, and this is the end of build, and this section is called as build-up section. Here, after this is called as tangent section or a pole section where you are holding the angle or you are maintaining the final angle at the end of build till you reach the reservoir. Okay, so in L profile you have one vertical section, one build-up section, and one tangent section, which is an L profile dashboard. And the next one is S profile. Even this is also have an L section, but instead you'll be having one more whole drop section. Okay, so see here you have a vertical section. From here you have kickoff point, then you have a build section, then you have a whole section or tan section, and then you have a drop section. So, for example, think that you have a salt dome or you have any kind of drill stock or anything else, and you have reservoir. So you are just deviating. You are just doing a vertical. From there, think that you have you have a salt dome. You have a salt dome. Okay, so you have to bypass this. So at that time, what I'm doing, I'm just going to come like this, and then I'm going to drop the angle. What is this drop section? I'm just going to decrease the angle at the end of hole section. Your end of hole will be the same angle at the end of build, right? So when I come here, I will just dropping the angle, which is called as S profile. Okay. So now we can see the next profile, which is a J profile. If you see this one, it doesn't have an S profile building or an L profile building. See here, you will be having a high vertical section. You have a large vertical section. From there, you will be deviating the well like this. You won't be having a whole section or a drop section. Okay, you'll be having just a build-up section. So keeping just a well built-up section is called as a J profile well. You won't be having a drop section or a tangent section. Clear? You'll be having only a build-up section, which is called as J profile well. Clear? Okay. So we have seen the application and we have seen the profile of directional drilling, right? Now we can see a design or a problem for a directional drilling. Okay. So in this, they have designed a relief well. Okay. You know about relief well, right? So you have a target well here. Suddenly you got a pipe stuck. From here, you are just going to a location which is beyond the vertical well, and from here you are deviating your well, and you are reaching the reservoir just to pump relief fluids in the vertical. Okay. So now how can we design this relief well by means of trigonometry? So you have around 8 steps to do this design. Okay, I'll explain one by one. See here, it doesn't have any amount of data for this. We have only 2 data, and rest everything is assumption. Okay, so in this problem they have given the coordinates, the UTM coordinates for your relief well as well as your target well. The ERD well is nothing but your relief well. It is ERD well is called as external drilling. I am not saying about it, but this well is your relief well. Okay. So the target well, the coordinates is this one and this one, and the relief well's coordinate is this one and this one. Okay. So with this you have to design your dash well. So what is the first step? Finding the distance between the ERD well and the target well. Okay. So what is the distance between the ERD well and the target well? How can we do this? By means of Pythagoras theorem. So see here, you have 2 eastings as well as northings. So if you do a left angle triangle, you can take this as east, right? So this is east and this is north, right? So you have easting coordinates as well as northing coordinates for both of your relief well as well as your target well. So by Pythagoras theorem, so d square, which is the longest part in the left angle triangle. So d square is equal to dn square plus d square, right? So with this Pythagoras theorem, we can find the d in the. So this is your dE and this is your dn and this is d, right? So by Pythagoras theorem, if you find this d, which is the surface distance between 2 wells, right? So d square is equal to dn square plus d square, which will get your final result of about 5453 meter. So distance between the relief well and the target well is 5453 meter at the surface. Clear? Okay. So that is the first step. We have finished the first step. And the second step is finding the 2 vertical depth when we have reached the end of well. So I'm just drawing your ERD well or your relief well. Okay. So this is your vertical section. Okay. The vertical section they have given as 200 meter. So from here to here it is 200 meter. That is given in the data. Okay. So from here we are starting your build-up section, right? So they are asking what will be the end of build. So how can we find the end of build? Tell me, how can you find the end of build? So true vertical distance is equal to this TBD, the true vertical distance from here to here. So before that, what is true vertical depth? Tell me, true vertical distance from the surface to the vertical distance from the surface to the end of reservoir or the end of any section, right? And what is this? I'll explain that to you. Okay, so MD is true vertical depth equal to this vertical section plus this section, right? So that is equal to TBD is equal to 200 plus, take this as B meters. Take this as B. Okay, take this as B. So 200 plus B meters. So how can we find this B? How can we find this angle? How can we find this straight distance? Tell me. So with the data they have given us, so at the end of belt you have 40 degree, right? At the end of belt you have 40 degree. And so you are taking this as true vertical depth from here to here, right? So if you are keeping, if you know this angle, right, B degree is 40 degree, right? Because the end of it is 40, so this angle will be here. So if you see as sin theta is equal to opposite by adjacent, right? Sorry, so opposite by hypotenuse. Okay, so sin B is equal to B by R. So sin theta equal to sin B is equal to B by R, right? So you want this B. So B is equal to R into sin B, which is 40 degree, right? So now we have to find this R. which is nothing but a radius of curvature, radius of this arc, right? So in this they have told you that the data have been given out. You can adjust the data of what they are telling that every 10 meters. I'm just taking it as an assumption. Okay, so every 10 meters you are increasing the build of about 3 degrees. You are increasing the build 3 degrees for every 10 meter in the build up section. Okay, so they are telling like every 10 meter you are going to build up or you are going to increase the angle of about 3 degrees. So with this you can find your radius of curvature. So R is equal to 360 divided by 2 pi into 10 divided by 3. Okay. So this is your meter, which is you are going to build up the angle, and this is your degree, how much angle you are going to build. So with this you can find your radius of curvature. So you will get one answer. Radius of curvature is equal to 191 meters. So when you find that 191 meter, so that is equal to R 191 meter, right? So into sine 40. So if you multiply this one, you will get your B answer for B. Here, which is 122.77. So when you get that, what is the formula for TVD before? TVD plus the vertical section plus B meters. B is like 122. So when you add both of it, you get the answer for true vertical depth at the build-up section. And what is the third step? Finding the measured depth along the borehole from the surface to the end of it. Before we have found TVD, what is this MD now? MD is nothing but a measured depth. So if you are drilling a vertical well, you'll be having, you're drilling a well, you have two depths. True vertical depth plus MD. So for the vertical well, your true vertical depth and the measured depth will be of same. Okay, but for a dash well will be different. True vertical depth is the vertical distance from the surface to the well. Okay, but the MD is the length of the borehole. Okay, so if it is a vertical well, true vertical depth, it will be from here to here, a straight distance. If it is a MD means it will be the length of the borehole. So we have to include the deviation part. So you will get the increase in length if you are considering a measured depth. So how can you measure this MD now? I'll tell you. How can you do it? MD, that is from here to here. So this section plus this section. You know this section which is 200 meter, right? The 200 distance from here to here is 200 meter, right? And then you have to find this radius of curvature, which is L. It's called as L. So how can you find that L? You can find this L by proportion, the angle to arc length. So normally, what do? You know the end of angle, right? End of angle of build, which is 40 degree. And also you know that every 10 meter you are increasing the angle to about 3 degree, right? So with that, by proportion, so you are having like every 10 meter you are increasing the angle of 3 degree, and then you are getting a 40 degree, right? By 10. Okay, so every 10 meter you increase the angle of about 3 degree, and here at the end of build you are getting a 40 degree, and you doesn't know the length, right? At which length you are getting this 40 degree, you doesn't know. So with this you can get this L. So L equal to what? 40 into 10 by 3. Right? So if you are getting that, if you are solving this one, you will get your answer, which is 133.33 meter. So what is MD now? MD equal to 200 plus 133.33 meters, which is 333.33 meters. Right here? Okay. So now we have found TVD and MD at the end of it. So what is the next one? Finding the horizontal displacement, right? Finding the horizontal displacement from the relief well reached at the end of well. So what is that? Horizontal displacement is this one. So what is this? So here it's a end of well, right? The horizontal displacement is the vertical well to your end of well. The horizontal, I want this part. Okay, the horizontal displacement from the vertical well to the end of well. So how can I find that one? Okay, if you are saying about cos B, what is going to be cos B? Adjacent by hypotenuse, right? Adjacent by hypotenuse, which is cos B is equal to, you include the whole section, right? So it will be like R minus, it will be like this area, right? So I want this, only this area. So it will be like R minus S divided by R. Okay, so if you know this B, right, and you also know about this R. So with this, you can find this H. So how can you find this? So if you're taking this R here, then it will be like R of B is equal to R minus H, and you know this R, right? So with that, you can find your horizontal displacement at the end of it. You can find this H, which is 44.69 meters. And the fifth step is at what depth would the ERD well or the relief well intersect your target well. I said that if you are drilling a relief well, it won't reach the reservoir. Instead, it will reach the well. Right? So here they are asking at what depth your relief well will intersect your target well. Okay. So how can we do that? So you are just taking the I, your intersection as I. Okay. You are taking the intersection as I. This one. From here to here, the intersection is I. So the intersection is I is equal to TBD plus P. Okay. So you know that P, true vertical distance from surface to end of well, right? And you are just going after the end of well, you are taking the true vertical depth from here to here. The intersection as P. Okay. So the true vertical depth is the intersection is equal to true vertical depth plus this P distance. So how can you find this P now? How can you find this P? It is very easy here. See here, you know this end of well angle, which is 40 degree, right? It is going to maintain the angle at 40 degree. So if you are just taking this as a right angle triangle or a left angle triangle or whatever it is, it will be like, if you are taking this as an angle, it will be like 90 degree, right? So 90 minus 40, then what will be it? It will be 50 degree, right? So if you are taking as tan 50, what is the tan 50? Tell me. What is the tan 50? So tan P is equal to P by H is opposite by adjacent, right? So P is equal to A tan P. Okay. So P is equal to, so this P is equal to A into tan P. Okay. So what is I now? I is equal to 200 plus this P. Here I can substitute that value for P now. A into tan P. So what is the make A now? A is equal to D minus H. And you know that the surface distance of target well as well as the relief well at the start we have find at the first step itself, which is D, right? Which is like 5453 meter, right? I think so. Yeah, 5453 meter. And we have find the horizontal displacement from the vertical well to the end of well, which is 44.69. 44.69. So when you subtract the first distance with this, you will get your distance from here to here, which is 5408 meter. So if you are getting that, you will get your what? The P distance. Okay. Fine. So I said that P is equal to the degree for P is equal to 50 degrees. So when you substitute this 50 here, you know A. So P is equal to 5408.31 into tan 50, and you will get the answer for the intersection. P is equal to 6460. So when you add this to this one, you get your intersection depth of your relief well at the target well. Here. And the final section is, what is the length of the tangent section of the borehole from the EOB to the intersection and the total length of the borehole? So we know about tangent section, right? What is the tangent section? The section at which you are holding the final angle of your build-up section. You are not going to increase the angle, you are just going to hold the angle at the end of build what you have. Okay? So this is your tangent section. Right? So I want to find the length of the borehole from the EOB to the tangent, to the well at which we reach the target. Okay. So you know about the you will be having a DV here, right? This is your tangent section, and you will be having this one, and you know P. This is your P section, and you will be having like 50 dV here, right? Which is a small P. And you know this A, right? And this, you take this as T. It is coming like this. You will be having your, you are having your build-up section like this, and from here you are starting your tangent section. You are taking this as T. I want this T section. I want this length from here to here, right? So what I am doing, what is sine theta? Sine theta is equal to opposite by hypotenuse. So I'm just taking like this. So I'm taking like, what is sine theta? Opposite by hypotenuse, right? So sine 50 equal to P divided by T. I want this T. So T is equal to sine 50 into P. We know what is P, right? We have found out, right? P is equal to 6,446.70 into sine 50. So when you found this, you will get the answer of about 88,415.62 meters. Yeah. Now we have found the length of your tangent section. So what is the final section right now? What is the length of the total borehole? What is the measured section of the total borehole? It is like you are having the section like this, right? Okay, so you have the section like this. You have your relief well like this. So what is the total length of the borehole? It is the length of section 1, the length of section 2, and the length of section 3. The vertical section plus the measured depth of your build-up section and the measured depth of your tangent section. Yeah. So that is equal to 200 plus L plus T. That is 8,748.95 meters. Are you clear with this? So, maybe I have any doubts? That's all. Now we have seen the design of a relief well or directional well. You can say anything about it. Tomorrow I will take another one for a design of a ERD well. Okay.